So a very good morning to all of you, and I hope everybody is fine, everybody is enjoying. And in continuation to our last discussion in which we talked about Hilbert space, we came up with some of the fundamental properties of state vectors that must exist if you deal with a problem linked with Hilbert space. And now I want to extend basically the same configuration but in a simplistic mode. And this is described by the famous Dirac, as all of you know, and he came up with an abstract way of writing the states, which we call as Dirac's KET-BRA notation. Now, before we go into the actual symbolic representation of Dirac KET-BRA notation, let me quote the first example. See, we are doing science, we are doing physics, we are doing quantum mechanics. And if you want to be powerful in this subject, you have to be imaginative in nature. You have to work out with respect to the imaginations. So to understand these symbols and to understand the products that we have using these symbols, I would like to imagine. Suppose I imagine that we have two singers. You understand the singers. They have to sing the same song. The music they are going to play is sing. They are in the same room. Would these two players produce the same kind of music? Even though their songs are identical. Maybe the instruments they are using are identical. Now, so I have two characters. Let me assume that I have two characters, character A, character B, and they have to sing the same song. Now a third person enters the room, and the third person is the listener. He has to listen. And both the players are playing the song, the same kind of song. Now at times, the song becomes absolutely powerful. It lights up. And at times, the song disappears. So what does it mean? It means it's not like that you are differentiating the song of one person from the song of another person. You are trying to see that to what extent the song of one person will be at harmony with the song of another person. To what extent the music that's produced by A merges into B, and to what extent the music produced by B merged in A. Now try to think about it. Now, if you find that the result is silence, if you find that the result is a silence, that means A and B, the music, same kind of music, same kind of song, but the result is what? Silent. What does it mean mathematically? It means orthogonality. It means, you remember the orthogonality condition. You have the two states. When you multiply them, the result is 0. And at the point you find the flashes of harmonious music, that's your normalization. You see that value? What's that? You take the product of the two states, what do you get? You get 1. You get the maximum. But is it all about 0 and 1? Is it all about 0 and 1? Then it's classical. No, it's not all about 0 and 1. It's about all the possibilities now. How much A's music can coincide with the music of B? How much the music of B can coincide with the music of A? Are you getting that idea? Now, to further understand, let's take another example. Suppose, let's imagine that I design a telescope. And you know what a telescope is. Using a telescope, what we can do is we can have observations. And my target is to see the stars. Right? Now, I design a telescope, I take it in the laboratory, it's installed, but this telescope has certain tones. It can read certain sounds. It can read certain signals. And it cannot read some other signals. Now out there are what? Out there are stars. And I'm pointing my telescope towards the sky in some particular direction. Do I see all the stars? Now what's happening? Now your resultant is based on the sensitivity of your device and the signals that are released by the stars. Those stars whose signals match with the sensitivity of my telescope, I'm able to see them, I'm able to observe them. And there are stars, they are also producing the signals, but the signals they produce, they do not match with the signals that the telescope has. And for this telescope, those signals are absent. You cannot see those stars. This is what gives us the measure of the inner product. You remember the inner product? Okay? The inner product between the two states. And we are going to do the same thing in terms of Dirac, KET-BRA notation. But the point is that you have these two states. By taking the inner product of the two states does not mean 0 and 1. It's a combination. It's a superposition. The inner product is giving us the measure of the superposition. To what extent A can match with B? To what extent B can match A? Let me take the same idea to the consciousness. Suppose I lived in a village. I lived my life as I was a child, and there was a spot where I used to play with my friends, with the fellows. So those memories remain. Okay? Now I left this village. I moved outside, and I came back to this village, say after 30 years. And when I see this village, I find everything is changed. I'm not able to comprehend. I find a building, I find another building. But when I reach to a spot where I used to play, and I'm able to find it. When I find that place, how do I find that place? I find that place when there is a superposition of my past, when I was playing in that ground, and the present. And what I remember about the past, is it exact? No, it's the superposition. It is the superposition what I did in those moments of my life and what am I thinking right now. So there is a quantum mechanical inner product going on between my present and the past. To take you more close to the concept, I have a room filled with locks. Every lock has a different key. And there's a traveler. This traveler holds a key. Okay? This traveler will use this key. In certain cases, the key will move a little bit. In certain cases, 30%, 40%, 50%. So what's happening? There is matching. There is inner product. It's an inner product between the key and the lock. And maybe finally you find a lock in which the symmetry of the key exactly matches with the symmetry of the lock. And the lock is open. And what's that? That's normalization. Are you getting my point? So there are infinite levels of information that we can perceive when we take the inner product of the two states of vector. Now what we have? We have the states, we have the state vectors. We talked about the Hilbert space. And what we're going to talk about is the Dirac KET-BRA notation. And for that, I will choose a state vector. Right? And this state vector, the choice is yours, say it is zeta. Now, if I put a bracket kind of thing like this, and like this is called KET. It's a notation. It's the notation of the state that you are talking about. It's a KET that is existing in your Hilbert space. And you can see its notation. It has a bracket kind of thing over, then you have the state, and it's closed by this line. Now this is also called as KET space. Now corresponding to every KET, there is another state vector which is called as BRA. It's called as BRA. So BRA is, so what I have the state zeta, I call it KET space, and I have another state BRA of this state vector. This is called BRA. This BRA is also called dual Hilbert space. So corresponding to every KET, there must exist a BRA, right? So this is a notation. Now here the choice is yours. You can choose any symbol here to represent a KET, okay? You have to be independent of that. I have chosen zeta here. So this is a KET. So this KET belongs to the Hilbert space, right? And it's also called as KET space. And corresponding to this KET, I have a BRA, and this BRA belongs to the dual Hilbert space. Okay. Now, Let's go with some of the important properties. Now, if alpha is any scalar, I take it on this because I am choosing zeta here. This is alpha is a scalar. When you multiply this scalar with the ket, what you will get? You'll get alpha zeta. But in dual Hilbert space, what will be this? This alpha will become star. I should write it inside. Its corresponding bra will be like this. Zeta, and here you will write alpha star. So this is the state ket with a scalar multiplied to it. In the bra space, if this alpha is a real number, it will remain alpha, but if it's a complex number, you have to be careful, you have to take the star of this. Right? Okay. Now, another important thing. Suppose I have alpha. No. Suppose I choose another state, phi. Okay? So if I have the ket of zeta and multiply it with the bra of phi. Right? This is ket of zeta. This is bra of phi. Now the phi that I have chosen, it should also exist in the same Hilbert space. It cannot be outside that Hilbert space. Right? Now this will form a bracket. Now if I choose I number of kets and j number of bras, what do you find here? This is the inner product. This is the inner product between these two states. And this inner product is going to give us the information that I was talking about. How much zeta i's match with phi j's. You remember the stories that I told you? The product between these kets and bras, they give us the measure of how much A matches with B. How much the signals that are coming from the outer sky match with the sensitivity of the telescope. How much the key that you are using in a room which has a large number of locks in it so that you can open a lock. That measurement is given by this inner product, right? And what is this? How we can write it in short form? We can write it as delta ij. We can use a chronicle. Chronicle delta. Chronicle delta. And how can you move on with this product? Now this phi j and zeta I will be equal to 0, for I is not equal to j. Am I right? So in that case, you will have phi I zeta I kind of thing equals not, it is not. It has to be j. It has to be j and it has to be I. Okay, I'm sorry, I committed the mistake. And this thing, phi j zeta I will be equal to 1 for I is equal to j. So this is what is called as orthogonality. See, you are writing it in some simplistic form now. Right? And this is called what? Normalization. Normalization. So the bracket that I have written here for these states will lead me to what? It will lead me to orthogonality. Orthonormality. And I can write down this orthonormality now as phi j zeta I is delta ij. And for this, what is important? Yeah? What is important? That I should be equal to j, you will get normalization. For I not equal to j, you will get orthogonality. Okay? So this is how you can write the inner product between the state, the KET states and the BRA states belonging to the same Hilbert space. Alright? Now, okay. Now if I write something like this, zeta alpha psi 1 plus beta psi 2, this is one way, and this we can write as, in this case, alpha will come out as star, and I should keep it like this. No. In this case, alpha will come out as alpha. Now see, I can write down this combination as alpha zeta psi 1 plus beta zeta psi 2. Am I right? This is how you can write it. But if I do its reverse, maybe I have done it wrong, I'm not sure. You'll check it from the book, okay? But if it is reverse, what it will be? If I choose now alpha zeta 1 plus beta zeta 2 and psi. In this case, the result will be alpha star. Alpha star, then you will have zeta 1 psi plus beta star zeta 2, here it's zeta 2, zeta 2 and star. It's clear? Right? Okay, fine. Got it? Okay. So now we can have something like this. Suppose I have alpha zeta 1 plus beta zeta 2 and alpha psi 1 plus beta psi 2. I can differentiate this as alpha 1, beta 1, alpha 2 and beta 2. Come on, do this product. Come on. You can do it. You will choose the previous two properties to get the product. Yes. Come on, come on. You do it, I'll also do it. So what I'll have, I will have, the first thing will be alpha 1 star and then alpha 2. And then you will have zeta 1 and psi 1 plus, then you will have, yes? Alpha 1 star, you're right, alpha 1 star, beta 2, then you will have zeta 1 and psi 2, zeta 1 and psi 2, then plus, yeah, come on, I'm relying on you, yeah, alpha, beta 1 star, beta 1 star, alpha 2, zeta 2 psi 1 plus beta 1 star, beta 2 zeta 2 psi 2. Okay, this will be the product between these two states. Okay, I think here we'll stop. If anybody has any questions, we can have a discussion on that. Come on. Come on. Hello. Anybody? So. Okay, let's continue the discussion, the mathematical discussion on Dirac's KET-BRA notation. And we have already gone through some of the important properties of Dirac notation, and we have taken up some of the important algebraic equations as well, where we try to understand that how we can move these KETs and BRAs. So now, ahead of that, what I would like to do is I would like to demonstrate using Dirac's KET-BRA notation the completeness of what we call as the completeness of Hilbert space, right? So to do that, what I'll do is I'll take on a state. Say for example, yesterday we chose what was the symbol that we chose yesterday? It was zeta. Okay, so I will choose the state zeta. So I'll choose a state vector. So I'm going to talk about the completeness. So we'll be using Dirac KET-BRA notation here. So I'll take a state vector. So I'll start with a state vector, and let me assume that state vector is zeta. Okay? As all of you know that you can write down a state vector in a Hilbert space as a linear combination of some other basis vectors. Okay? So I would like to do the same thing. So I have a state vector, say zeta. This is equal to summation. Okay, you have the summation. You may run it from I is equal to 1 to n. Then you will have some coefficient, say ci. Then let me choose another function as phi I. It's ket. Okay, so you have the ket of zeta. Okay, it's a state vector. You are writing this state vector as a linear combination of ci's and phi i's. But you can see here, this phi I is what? Is the ket. It's ket of all those phi's that are existing in the basis vector space. Right. So if this is the case, so this is my starting equation, because the target is to demonstrate the completeness of the state vector in the Hilbert space. So what can I do now? So I would like to write it again. So what I have a state vector zeta, and I write it as a linear combination of ci and phi I kets. Now what I do is I introduce another basis vector. And what is that? So I introduce another vector as phi j, but the bra of phi j. We have already talked about it. We know what ket means, what bra means, okay? So there's nothing new in it. So what I do is I have chosen another basis living in the dual Hilbert space, right? And I symbolize that as bra of phi j, right? Okay, now what I'll do, I will multiply this to the other equation, right? From left. So order is important here. So what I'll do, I will write bra phi j, and zeta will be equal to sigma bra phi j. You will have ci and phi I. Is it right? Am I doing it right? Come on.
Yes.
Okay. So now you can see what is Ci. These are numbers. They can be complex numbers. They can be real numbers. So this Ci will come out. So what you'll be left with? You will have the inner product between phi j and zeta. This is going to be equal to sigma Ci, I think, is out. So inside you will have phi j and phi I. Right? Okay? Now see, it's becoming very simple to do the same thing that we did in the previous case. So what's going to happen here? Now you have an inner product between phi j and phi I. So what is this inner product? This is phi j and this is phi I. This is a canonical delta. Phi ij. Now this inner product will exist only for I is equal to j, isn't it? So if this inner product exists only for I is equal to j, what will happen to my left hand side? It will become the BRA of phi I zeta equals sigma Ci. Am I right? That's fine. Okay, this is the value of the inner product, okay, between the basis vector that I introduced in the dual space as phi j. I can write down it as phi I. So this inner product is sigma Ci. Let us go back to the original equation. What was the original equation? It was the state zeta, and you wrote it down as the sigma Ci, the ket of phi I. This is what you did, isn't it? Right? This was something that you started with. So we have already calculated this sigma Ci, right? And what's its value? So what I have the state zeta. Now what I'll write for this Ci, I'll be writing sigma, it will be the ket of phi I and zeta. And then you will have phi I. Come on, look at it closely, isn't it? Right? Because this is already calculated. You have written down that constant in terms of the inner product between phi j and zeta. Right? So now let's do a little bit of exchange. Now if I write this phi I can do that. I can write down this ket here, phi I. Okay? I'm writing this first. What will come after this? The BRA of phi. Okay? So then I write BRA of phi I. Are you getting? And what's coming the last? Zeta. Isn't it? Now, what is this? Now, if you have something like this, suppose I have some state zeta and I have the state zeta. This is also a product, but we call it outer product. What it's called? It's called outer product, right? So what we have zeta equals sigma, then we have phi I, then we have phi I, and then we have zeta I, right? You started with zeta, you wrote down it in terms of a basis vector. It was in terms of phi's, you remember? And you are getting the final equation in terms of zeta. Are you getting my point? You remember the completeness that we discussed in the previous case? So what should be this? In the previous case, what we had Dirac delta. You remember?
Yes.
You had Dirac delta and the original vector, right? And here you have an outer product. What this outer product should be equal to? Yes, you're right. Somebody said right, I think. Yeah? Yeah? Come on, come on. You remember, you can check your copy. When we talked about the completeness, using the inner product between the two states, then finally we obtained our state vector in terms of the same vector. And we introduced Dirac delta. And the beauty of the Dirac delta is that it gives you 1 for I equal to j, right? And at all other values, the value of this Dirac delta is 0, right? So what should be the value of this outer product? How can I write down here so that my vectorial equation is alive? If you'll say 1, that will look so bad. You are in the world of vectors. Yeah. Identity vector. So this outer product that you have, this is identity vector I. So phi I and phi I. So the property is verified. Completeness. We have again verified the completeness of the state zeta in the Hilbert space, right? Because you are able to get your state vector in terms of the same state vectors. So this defines the completeness. Okay? So here we would like to stop here and then we will look for another interaction. So you stop it.